So we start with the chapter linear models. But before linear models, let's do some short introduction into math modeling. So I will use a diagram which best describes what's math modeling about. So this is this diagram. I've already explained before a little bit, but let's repeat now in a more precise way. So we start with a real world problem. And of course, there are too many parameters to take into account when solving such a problem. So we have to do some simplification. We try to extract the most important properties of this real world problem, and we get idealization. So in this idealization, only those things which we think are the most important are taken into account. And now when we have this idealization of the problem, it's easier to be handled, and we can build a mathematical model out of this idealization. So in this idealization, there are some things which vary, and those things which vary become our parameters. And we build a mathematical model which is dependent on some parameters. And as we will see later, this model can be linear, non-linear, or it can be dynamic. I've already said that linear model only includes our parameters to the raised to power 1. Then non-linear model includes our parameters raised to higher powers, or even includes the transcendental functions of our parameters. And then the dynamic model also includes some derivatives of our parameters. So once we've chosen our model, so this model depends on some parameters, we have some data, and we would like to find the values of those parameters such that our model fits our data in the best way. So what does this mean, that it fits the data in the best way? Probably already know this notion of least square fitting. So this means that the mistakes of the data, so the mistakes between the model and the value of the data squared and then summed together is the smallest possible. So in each data point, we measure the mistake, the error, square it so that we don't have cancellation of pluses and minuses, because in one point we could have error +1 and in the other point -1. And if we just sum this together, then we get that the error is 0, but it's not true. The error is 1 in one point and -1 in the other point. So all together, the error is 2. That's why we square those errors. So we square the errors and sum them up for all the data points. And so we are searching for the parameters which minimize the sum of squares. And this means that we are searching for the solution with the method of least squares. So this is our task, to find the parameters which minimize this error. And this can either be done directly. So we solve this analytically with the aim of some mathematical techniques, and we come to the solution, we come to the values of the parameters. But most of the time, this won't be the case. most of the time we won't be able to solve our problem directly because it involves too many data and too many parameters, and we will have to use mathematical mathematical programs which will calculate approximate solutions for us. So we will write a program and then do a simulation with the computer. There are different programs which can be used, but in this course we will mostly use, and in lab sessions you will only mostly use Octave or MATLAB. So those computers use different integrated methods, mathematical methods, to find approximate solutions to our problem. Okay, so we are here, conclusions. So in some, now we got the values of those unknown parameters, either directly or via computer. And now we have to ask ourselves, does the solution make sense? So does the solution explain this real world problem? So does the solution behave as expected from our real world problem? And if yes, then we are happy. But if not, we should think about where in this diagram the problem occurred. So either was this simplification not good, so did we simplify the problem too much, or did we miss the most important component of the problem? So this is first source of mistake. Then the second one is whether we used the wrong model. So here we choose whether we will use linear model or non-linear model, and there are a lot of linear models, a lot of non-linear models, a lot of dynamic models, and we should ask ourselves, was our choice correct? Or do we have to include other parameters or change our model? So this is the second source of errors. And then the third source of errors is whether we did some simplifications when solving the problem analytically, or whether we did a mistake in using mathematical tools, or if we used computers, whether the problem was because of numerical mistakes. So you know, the numbers in computers are floating points, and we are only limited to finite number of decimal places, and we just all the other decimal places from somewhere on, we just forget about them. And sometimes this can be also an important source of the errors. So these rounding errors, this is one case, so rounding errors, but the other is that our problem, so we have our model, this model could be ill-conditioned, which means that whatever method we use, we cannot expect to get a good solution because the problem is ill-conditioned. And I will say something more in a minute. So just be aware that when we try to explain why there was an error in our solution, you have to take into account those three types of errors. So simplification, to simplify things, or wrong mathematical error model, or wrong analytical tools, or rounding errors. So those are types of errors we could do. So are there any questions? Okay, let's proceed then. So before we start with linear models, I would like to tell something more about these ill-conditioned problems and the mistakes, the numerical mistakes which we can do when solving a problem. So what does this mean? What does this refer to, that the problem is ill-conditioned? So types of mistakes, types of errors when solving our problem. And this refers to types of numerical errors. So the first is that the problem can be ill-conditioned. I will put this into the parentheses, and I will define shortly what this means. So what does this mean? What does this mean that the problem is ill-conditioned? So this means that changing our data just a little bit can have a great impact on the solution. Changing our data just a little bit can have a great impact on our solution. And there is a simple example. We have two lines, and we would like to calculate their intersection. And let's say that we have one line which is like that. So let's say line 1, and then we have another line which is like that, line 2. And we would like to calculate this intersection. This is what we would like to determine. So this is only a system of two equations, of two linear equations. And there are two parameters because L1 is of the form, so L1 of x is ax plus b, and then L2 of x is cx plus d. And we're calculating this intersection. And now we change the data only a little bit, meaning that we change a and b to a tilde and b to b tilde. And let's say that the same for c and d. And the question is, what happens with our intersection? So with this new data, our lines change a bit. So for example, this L1 becomes this, and then this L2 becomes this. And the new intersection is this point, P tilde. And from the picture, we see that the intersection didn't move a lot. So relatively, so the change in the intersection is relatively small. So in this problem is not ill-conditioned. So this is well-conditioned problem. Because if we change our data just a little bit, then the solution also changes relatively a little bit. Well-conditioned problem. But the other problem is if we would have two lines which would be almost parallel, and we are solving the same problem. We are searching for the intersection of two lines which are almost parallel. So let's say that this is L1, this is L2. Okay, on my picture they are not almost parallel, but they should be. You can try to draw a better picture in your notes. So this is L1, this is L2, and let's say that this is intersection. And again, we change those lines just a little bit. Let's say that L2 becomes this. And then L1 becomes, can we change L1 a bit? Just we change A and B to A tilde and B tilde, and C and D to C tilde and D tilde. And we see that this intersection changes a lot, relatively a lot. And this is what we don't want. So just this tiny change in the data, which can be either caused by wrong measurement or because of rounding errors. So only tiny change in the data completely changes the solution. And this is ill-conditioned problem. And if we are dealing with ill-conditioned problem, then whatever method we use, we cannot get more precise solution than this P tilde. So already because of the mistakes, in the data, we do a lot of error, and then we also do a numerical error or a mathematical error, and this P tilde will be even more far away. So we cannot expect to improve this error with our method, because it is there. So this error is incorporated already in the problem. So we don't want to solve ill-conditioned problem. If we have ill-conditioned problem, then we have to reformulate it in some way to make it well-conditioned. So this is the first thing which I would like to stress. So if we are dealing with an ill-conditioned problem, then the error will be big, whatever method we use. So the first requirement for our course is that we have well-conditioned problem. So we will be we'll be solving well-conditioned problems. So that really the biggest source of the error is our method. So this was the first type of the error. And then the second type. The second type is numerical error. Caused by rounding. So there are two ways how to deal with this numerical error. So one way is to change the method, change the model, or change the method, change the method we use. And the other way, if the method is not the biggest source of the mistake, we should at least know how to estimate our error. So know how to the error, the numerical error. So what does this mean? A numerical error caused by rounding. So we have some x, which is floating point. Let's say x is 0.1, and then something 2, 4. If we do in the 10-digit system, if we work in the binary system, then we have only zeros and ones. But let's say that we are in the 10-digit system, so we have 1, 2, 4, 5, and so on, 7, 8, and so on. And because we are limited only to finitely many places, from somewhere on, we just cut the remaining part. So let's say that from here, we just forget about this part. And it seems that we didn't do a big mistake with forgetting this. So let's say that this is on the 52nd place. So our error was at most, so error is at most 10 to minus 51. So it looks that this is not, this error is not big. However, when we subtract, we will see that when we subtract two numbers which are almost the same, and then do further calculations with them, then the final error could be really big. And there is one nice example. Solving quadratic equation. So let's look at this example to demonstrate that really this can cause relatively high, relatively big error. So let's say solving quadratic equation. We have x squared plus 2a squared x minus q is equal to 0. Why I used here a squared instead of just a, just to stress that this coefficient is positive. That's why I used a squared. So we all know how to solve such a quadratic equation. There is a formula to get both solutions. Let's remember this formula, x1, 2. This is minus this second coefficient, so minus 2a squared. And then we have two options, plus, minus, square root, and then we have the discriminant. So it's the second coefficient squared. So it's 4a to the power of 4 minus 4ac, so 4 times first coefficient times the last coefficient. So in this case, it's 4q over 2. And if you just divide by 2, we get minus a squared plus minus a squared plus q. And we are, there's one question. Thank you, a to the power of 4. Thank you. Here in the under square root, it should be a to the power of 4. So if we try to calculate both solutions with this formula, then one of them turns out to be non-stable. So I've mentioned here, when we do calculations numerically, we just forget about decimal places from somewhere on. And then the problematic operations becomes subtraction or addition of numbers which are almost the same. Why? Because when we subtract or add numbers which are almost the same, then this part, which is not here, which is not omitted, is almost the same. And when we subtract two such numbers, we get on these decimal places, we get zeros. But on the remaining part, which was neglected, those two numbers can be different. And if we would do precise calculations, we would get 0 point something 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 times 10 to minus 52. So we don't get 0. And if we divide this by 10 to minus 52, we get something 9.8 point something. So we don't get 0. And here is where the problem occurs, because if you forget on those numbers, on those digits, and then subtract two numbers which are the same up to those neglected digits, and then do further calculations with them, then the error can be big. So calculating the solutions of this equation with this in this way, the non-stable operation is when we the non-stable method is when we take here plus, because when we take here plus and a is much bigger than q, then here we get minus a squared. And if a is much bigger than q, then a to the power of 4 plus q is almost a to the power of 4. And then we square root a to the power of 4, and we get minus a squared plus almost a squared, and we get almost 0. And then we plug the solution into our equation and calculate what we get, and we will see we don't get 0. So the question is this second part. So this second part under square root, it is so we have b squared. This is 4a to the power of 4 because b was 2a squared, and then minus 4ac. So c is here minus q, and a is 1, so it's 4q. Okay, then it's clear. Okay, so there wasn't a mistake, but please don't be shy. Just tell me if there is some mistake. So this time I think everything is correct, but next time probably it won't be. So just interrupt me. Okay, so this is the problematic operation, problematic method. And let's see that this is really the case, that we can get big errors. So let's take a squared equal to 10 to the power of 5 and q equal to 1. And let's use octave. So if you don't know octave, you will get to know it on the first lab session. So let's use octave to calculate x2 with this method. So this is octave. Here I write, so our a, I will just write, so big A, this will stand for a squared. So it's 10 to the power of 5. And then q is 1. And we calculate our solution. So minus a plus square root of a squared plus q. And I have to use format long so that I will have more digits, more decimal places shown. Let's say this is our x. So this is the solution. And now let's check whether this is really the solution of our equation. So our quadratic equation, if we remember, was x squared plus 2a squared x minus q. And let's plug this solution into our quadratic equation. And if the solution is correct, then we should get 0. So let's see. So we have x squared, and then we had plus 2a x, and then minus q. And you see, we got minus 1 times 10 to the power of minus 6. So this is not 0. It's small, but it's not 0. So MATLAB and Octave take numbers which are below 10 to the power of minus 16 to be 0. So this minus 1.1 times 10 to the power of minus 6 is not claimed to be 0 by Octave. And also for us, this is already the mistake on the sixth digit. So really, this method for calculating one of the solutions was not really precise. And the problem is, as I've said, the problem is in this rounding. However, since we are aware of the problems of our method, we can try to use another formula. So Octave says that it's our x is around, x2 is around minus 4.9 times 10 to the power of minus 6. But x2 squared plus 2a squared x minus q was not 0. It was around 10 to the minus 6. So how to solve this? We will try to use another formula, so another better model to calculate the solution. And one way is to, so this one, minus a squared, a4 plus q. We would like to get rid of this adding of numbers which are almost the same. So this is negative of this one. So how to get rid of this problem? One way is to multiply this equation by a4 plus q plus a squared. And of course, we then have to also divide by the same number. And why did I do this? The idea was to use these formulas that so a minus b times a plus b is equal to a squared minus b squared. So a minus b times a plus b is a squared minus b squared. And here I took, this was my a, and this was my b. And what I get, so in the numerator, I get a squared, which is just getting rid of the square root in a to the power of 4 plus q. So we get a to the power of 4 plus q. And then minus b squared is just a to the power of 2 squared. So it's a to the power of 4 divided by a squared plus square root of a fourth to plus q. And here a4 subtracts in the numerator. And what I get is another formula for calculating the same solution of our quadratic equation. And I claim that this is more stable. And why? So this is more stable because here we don't subtract two numbers which are almost the same. So we have a squared here and a squared here, but we add them. So we don't subtract them. So we don't, then those decimal places which are not neglected do not cancel. They're just doubled. So there won't be problems because of these errors, numerical errors. And let's check on our example. So where a squared is 10 to the power of 5 and q is 1. Let's check with Octave that we really get better solution. And then we will do a 15 minutes break. So our A is the same, Q is the same. And now we use this formula Q over, and we had, let's check me. So A plus square root of A squared plus Q. And this is our X. Yeah, we see that it's almost the same as the X from the previous method, but here on sixth place there are difference. From sixth place on, there the decimal places are different. And let's check if this X satisfies our quadratic equation. Yeah, you see that here we really got 0. MATLAB really gave us 0. That means that the first non-zero digit of this x squared plus 2ax minus q appeared far away, and therefore MATLAB takes it as 0. So here.
So one question, the problem with the error we got here was basically the rounding of the numbers.
Yeah, the problem was rounding of the numbers, yes. So because from somewhere on, the decimal places are neglected, and what we had here, so in the first method we had minus a squared plus almost a squared. So we were adding two almost same numbers. So this number and this number were almost the same on those this non-neglected part. Therefore, so the difference would be here, but we neglected this part because we cannot do it differently because we have only that many places which are used in computer. So this was the problem. But on the other, for the other method, we just used some analytical computations. So we didn't change anything from the analytic perspective. We should get the same solution. However, here we got rid of this subtracting of two numbers which are almost the same. So this a squared and almost a squared were not subtracted but added. So those decimal places doubled in the denominator. So the source of mistakes because of numerical mathematics is adding or subtracting numbers which are almost the same. Multiplying or dividing numbers which are almost the same is not a problem. The problem is only subtracting or adding. So here, with this formula, the solution was much better, So only the conclusion of this first introductory hour. So numerical problematic operations because of numerical errors are plus and minus. So the operations times or division are good from this perspective, are not problematic. Okay, and let's do a 15-minute break, unless there are some questions.
Yeah, just another quick question. Yeah. But we still in this equation had two numbers that are very close together, but we added them up.
Yes.
So how come there was no problem with that?
So here we have a squared and almost a squared, and we added them up. So since we added them up, so let's say that this is a squared, 0.1245 and so on. And then we added the same a squared. And so this part doubled. And this neglected part is still not important because this part which is not neglected doesn't become 0. If this part would become 0, then suddenly this neglected part would become important because it would move here to 0.9 something times 10 to the power of minus 51. So if this non-neglected part becomes 0, then this what became neglected suddenly becomes important. However, in the second equations, in the second method, this non-neglected part only doubled, so it didn't become 0, and the neglected part was still not important.
Okay, understandable. Thank you.
Thank you for the question. So in this course, we won't go deep into analyzing those numerical errors because this is not the aim of the course. You only have to be aware that if something goes wrong, then it might be because of the method, because of those rounding errors. But analyzing rounding errors is more under domain of numerical mathematics, which is another course. So we won't go into, this is only the introduction into analysis of numerical errors. Just keep in mind that problematic operations are addition or subtraction. And when we do this so when we add, the problem is when we add two numbers which are one a and the other minus a. And when we subtract, the problem is when we subtract two numbers which are almost the same. Maybe some other questions? Okay, then let's do a 15-minute break. So we start at 10:30. So we finished the first hour, the introductory hour, with the introduction of those numerical errors, which can be really problematic in some cases, especially when the operations are addition or subtraction. And we looked at an example where such error really occurs. This was this example of solving quadratic equation. But those errors really occur in the real world. And here I would like to stress two very well-known catastrophes caused by those numerical errors. Here I will show you the links. I will also put the links in the handouts, and you can look, you can read a little bit more about this, and there will be also a link to actual YouTube videos. So the first catastrophe was the explosion of the rocket Ariane 5. It was in 1996. And this rocket, so it exploded 40 seconds after launching. And the problem, after the analysis, it turned out that the problems were numerical. So the problems for explosion were numerical nature. So the problem was that the horizontal speed of this rocket exceeded the possible range of the so numbers which can be expressed in the given floating number system, in the used floating number system. And the exception was that in this case, the rocket should, so the machines should turn off. And this is what happened. So after the horizontal speed exceeded the maximal possible in the given number used, so in the given used number system, and this was the reason why the rocket then exploded. So they didn't, when they were modeling the speeds, the problem was that they didn't model this horizontal speed the rocket will really reach. And there is a actual YouTube video showing how this rocket explodes, and I will put the link in PDF. And another famous, in the negative sense, famous, of course, problem was the sinking of the gas station in 1991. So this is this gas station. They built it and tried to put it in the sea, 60 meters below the, so in the sea, which was of depth 60 meters. So they modeled the forces using some mathematical model. It goes for some system of partial differential equations. And of course, some simplifications have to be made to solve such a system. And it turned out that their simplifications simplify the situation too much, and the forces they modeled was smaller than the actual forces which occurred, and this caused that when they were building this station, it just collapsed. And there is also a video showing how this station collapses and falls into the sea. There will be also a link in the handouts. Okay, this was for the introduction, just that you are aware of the possible problems which can happen when we model some problem and when we are solving some problem. But now we will focus on the first chapter, which is, as I've already mentioned, linear mathematical models. So we will precisely define what linear mathematical model is, and we will look at one way of solving such a model. You probably don't know this model, this way of solving it. So it goes via generalized inverses, and we will look at some specific generalized inverses, so-called the Moore-Penrose inverse, and the properties of those inverses. But this will be so the material for the next 3 weeks. So let's start. So chapter 1 is linear mathematical models. So from now on, we will be given points. So we will be given points. And so points x1, y1, then x2, y2, and so on. xn or xm, ym. And those x's will be points in, so these will be tuples of real numbers. So this won't be a real number, but it can be tuple of real numbers. So x1, it is, so for example, x1 is 1, 0, 2, and so on. So it's a tuple, it's n tuple. And y will be just a value. So y's will be real numbers. And what is our task? So we would like to fit those given points with some function. And why do we want to do this? So we want to do this that we can also predict what's the value of y for some x which is not among those which are given. So we would like to know, given xm plus 1, what is the value of y? So given this, what is the value of y? That's why we would like to fit those points with some functions. Because for those x's, we already know values of y. The question is, what is for some other x, which is not between those given? So our task is to determine the function, determine a function, let's say big F, large F, which is dependent on those points and on some parameters A1 up to AP, such that yi is equal to f of xi A1 up to AP for all I from 1 to m. So those are parameters to be determined. Parameters to be determined. In such a way that the value of this function in each xi is precisely this yi. So if we write this in the long form, we should have f of x1 with parameters a1 up to ap. This should be y1. Then f of x2 at those parameters, this should be y2, and so on. This should be true for all points. Of course, if we have a lot of points, then if we would like to satisfy all those equations, then this function must be complicated enough. But we don't want that this function is too complicated. If you have 10 million points, then this function should have a lot of those parameters A1 up to AP. But we limit those parameters just to a certain senseful number. So let's say 10 parameters. So if you have only 10 parameters, you cannot expect that this fitting could be done for all 10 million points. Therefore, we have to a little bit relax this problem. So if we have a lot of points, it won't be possible to satisfy this system, to satisfy the system star. So we have to relax it. So we have to relax our requirements. Of course, it's possible to satisfy this system if the function is complicated enough, but we don't want f to be too complicated. So we rather relax our requirements, and the requirements are then not that we have equalities here, but we have some approximations. So y1 will be approximately f of x1 on the parameters a1 up to ap, and so on. So instead of equalities, we have here approximations. So instead of equalities, we require approximations that require that our system is approximately satisfied. And as we already mentioned in the first hour, this approximately satisfied will refer to the least squares method. So the system is approximately satisfied, and I will explain what does this mean. So the solution A1 up to AP is the best in terms of least squares, in terms of the method of least squares. So what does this mean? We look at the difference between y1 and the value of the right-hand side, and then we look at the difference between y2 and the value of the right-hand side, and so on. And we don't just sum those values, because some are positive and some are negative, and they could subtract. However, we square those differences so that we don't have this subtraction. So we could get, if we wouldn't square those differences, we could get 0 at the end, even though the actual approximations would be bad. That's why we have to square. So it's the best in terms of the method of least squares, meaning that this sum f of x1 a1 up to ap minus y1 squared plus f of the same for x2 a1 up to ap minus y2 squared, and so on. So it's the smallest possible. So this sum should be the smallest possible. In a compact way, it could be written in this form. So compactly, we just write sum over all points of this expression f of xi a1 up to ap minus yi and squared. So we would like that this is the minimal possible. Now I would only like to check if you're still following me. So we are minimizing this sum. Above what are we minimizing this sum? What are our unknowns? Can someone tell me what are our unknowns?
The y values.
So x and y are given. Yeah, so ai's are our parameters. So we're minimizing over all possible p tuples of a's, because x's and y's, those are our points which are given in advance. So we're given these points. Those are non-unknowns. So these are numbers, they are given. We choose function f, but this function f is dependent on the parameters a1 up to ap. So these are parameters to be determined. So these are unknowns. So in our model, when we say that we are minimizing this sum, we are plugging in all possible a's. Of course, we cannot do this to check all possible a's, because there are infinitely many of them, but we can use some method to determine those parameters which really minimize this sum. So I will just stress this. These are our unknowns. So we go over all. So I will put this into parentheses because we don't really go over, but minimizing would mean that we go over all possible a's, all possible p tuples a1 up to ap and see when the expression, let's say, circle is minimal. This is still a general situation. We have not specified that the model is linear by now. So the same setting would be true for the nonlinear setting and for the linear setting. But what does this mean that we are searching the linear model? This refers to this function f. So this function f is a function of a1 up to ap, and those points xi, which are given, and it's linear in those parameters a1 up to ap. So the model is linear when f is of the form so f of x a1 up to ap. This is a1 times some function of x. So this function of x doesn't need to be linear. So the important part is that this function f is linear in a's, because a's are the parameters which we need to determine. Those function phi1, this is just some function, and we can calculate the value of the function on a given x. Plus a2 times some function phi2 of x, and so on. ap phi p of x. So those functions phi1 up to phi p, those are some given functions which map x's into some values. Because you remember, x's were n tuples of real numbers. And in this model, if you know what are those phi's, we have to know them, yeah. We have to have them determined. So when we have these phi's determined, this is just some number, and this is just some number, and this is just some number, some coefficient. So this linear part refers to these parameters a1 up to ap. So they're just a1 to the power of 1. And no, so we don't allow higher powers, and we don't allow transcendental functions. So let's say trigonometric functions. So if we would have cosine of a1 here, then this wouldn't be linear model. So this linearity refers to those a's. You all know one linear model. Just think about, and can someone say where you met some linear model? So example, let's say that those x's are really real numbers. So if you have x1, y1, let's say that this is some point in the plane. x2, y2 is again some point in the plane, and so on. xm, ym is a point in the plane. So x1, y1, then x2, y2, x3, y3, and so on. Those are our points. And from statistics, you probably remember, yeah, linear regression, that's true. Or finding a polynomial. This will be also true. Let's first look at the linear regression. So from statistic, you probably remember you had points, and you had to find a line, the best fitting line through those points, And this was nothing else than a linear model. So this f could be written as, so this is some line L. Okay, let's write it as f. So this is line f, which is dependent on the value of x and on two parameters, a and b, and it is of the form ax plus b. And you are searching for this line in such a way that those sums of y I minus ai xi plus b squared, when you sum over all a's, is the smallest possible. And this is linear regression. So if we look at, if we compare this general linear model with what we have here, we can see that, so we have two parameters, a and b. So a corresponds to, let's say, a1, and b corresponds to a2. And we have here a1 is this a, and this phi y x, this is just x. So here phi y, phi1x, this was just x. So this function phi1 of x was x. And then phi2 of x should be here, but it was just 1. So phi2 of x, for every x was 1. And all the other, and this is all what we had. So we had two parameters, a and b. So we need only two phi's. Phi1 of x is just identity, it's x, and phi2 of x is just a constant, it's 1. So this linear regression can be seen just a special case of this linear model. So in this linear regression can be generalized so that we don't require this fitting function to be a linear function, so to be so that those coefficients are dependent. Of course, we require this f to be linear in terms of a and b, but we could require those coefficients can be also higher degree in excess, in which case we are talking about polynomial regression. So this was linear regression. But we could have more parameters. Of course, then I cannot write the picture in the plane, because if we have more than two parameters, okay, if we had three parameters, then I would need to use r to the power of 3. But if we have more parameters, then I cannot draw a picture. So a general polynomial regression is what I cannot draw, but still we have the same setting. We have points in the plane. But I allow more parameters. But now I allow more parameters, let's say p parameters. A1, A2, up to AP. And then our function is just A1 times, let's say, x1 to the power of p minus 1 plus a2 times x1, so times x to the power of p minus 2, and so on. P times 1 at the end. So in the linear regression, I only had two parameters, and I had ax plus b1. I could also draw this fitting function in R squared. But if I allow more parameters, of course, then I can get a better solution. But then this model is a bit more complicated. So we have here polynomial regression. We have phi1 was phi1 of x is x to the power of p minus 1, then phi2 of x is x to the power of p minus 2, and so on. So this is polynomial regression. So phi1 of x is here x to the power of p minus 1, and phi2 of x is x to the power of p minus 2, and so on. Phi p of x is 1. There are two comments in the chat. Yes, we just change f of x is ax plus b to f of x is of this form, as I wrote, or as you wrote in the chat. Yeah, and then when solving such a system, then we can do partial derivatives with all. So we can do when we minimize. So here, when we minimize this function, so one way of doing it is to just taking partial derivatives with respect to a and partial derivative with respect to b. And since we want this to be smallest possible, both of those partial derivatives have to be 0. Only two partial derivatives. Here we have only two partial derivatives. But in this polynomial regression, we have p parameters. And I won't write explicitly this function f, but it's of the same form, yi minus, and then we have this expression evaluated in xi and squared and summed over all numbers. And to find the minimum, one way is just to take partial derivatives and set them to be 0. But there are also other ways on solving this system. We won't solve this system via partial derivatives. We will solve this system in terms of generalized inverses. So we will come to this topic already today, and then we will also deal with this topic for two more weeks. Okay, this is one example, linear regression. The other example is polynomial regression. And here we fixed x's to be real numbers, but if x's would be, as was stated at the beginning, so it was if x's were tuples of real numbers, then this function f would not be of the form ax, but would be of the form a1 x1 plus a2 x2 plus x3 a3 x3 and so on. So for each coordinate of x, we would have one parameter. Still, this f would be of the same form, only that there would be more x's and consequently more a's. And we would be dealing with multilinear regression. So linear, but since we have more variables, it's called multilinear. And you can find explicit formulas in the handouts. I will show you what I mean. So you see, linear regression is what we did. Then polynomial regression is also what we did. And then multivariate linear regression or multilinear regression requires, so we have tuples of x's, and for each of those x's we have its own a, and then those phi's are just so phi 2 refers to a1 x1, and then phi n refers to an xn. But we could also allow more complicated phi's, for example, trigonometric functions, cosine, sine. In this case, we are talking about frequency analysis. Again, I won't write equations specifically when we will need it, or when we will need it in lab sessions. We will look at the specific case of this model. Just note again that here we allow trigonometric functions. Before I said that in linear models, we don't allow trigonometric or transcendental functions. But the fact is that we allow trigonometric functions referring to those phi's, but we don't allow that here. We would have cosine of a1, for example. So here it should be linear in A, but those phi's could be as complicated as we want. So if we think that for the specific real-life model, specific phi's will work, then we can take those phi's in our model, and still we deal with a linear model. And here is an example when the model wouldn't be linear. So if f of x ab is a times e to the power of bx, this is not linear model, because, okay, a still appears like here, but phi of x, this e to the power of bx, is not a function of x solely, but also of this second parameter b. And this is what we don't allow, because then the model is not linear anymore, and what we will look in the continuation won't work to solve such a model. So other ways of solving such a model will be needed, and this will be seen in the second chapter. And here is another example when parameters occur in a nonlinear sense. So it cannot, this function cannot be written in this way. Okay, are there any questions?
So if we use the example with phi's on the example of the linear regression we did, it would just be like phi 1 would be 1, so that would correspond to b in the equation, and phi 2 is x, so ax.
Yes,
okay,
exactly. I just switched the order of phi 1 and phi 2 above. But yeah, as you said, phi 2 would be x, and phi 1 is 1. Or vice versa, if you take another order of a's and b's. Okay, let's proceed for another 10 minutes and then do a short break. Okay, now we have our data, x1 up to x1, y1 up to xm, ym. We've chosen our linear model f. And so we have our equations. So we have, let's return. So we have our data, x and y's. we have f. We have chosen it in a way that it's linear. That means that f is of the form a1 phi 1x plus a2 phi 2x and so on. And then we get this system star for this specific f. And since the f is linear, we can write this system in the matricial form. And this will allow us to use matricial techniques to solve such a system. And let's do this. So let's repeat. So we have x1, y1 up to xm, ym. These are our data. So x's are from n tuples of real numbers and y's are just real numbers. We have our model. Let's say that we have p parameters and our model is linear. So it's of the form a1 phi 1x plus a p phi p x. So we have a bunch of equations. We have m equations. So our system star is then, I will rewrite it so that you it will be more clear how we build a matrix form out of the system. So we have y1 is f. Y1 is capital F of x1 a1 up to ap. And for this specific f, it is y1 by 1 x1 plus ap phi p x1. And the same for the other points. So y2 is f of x2, and then again these parameters. It's a1 by 1 x2 plus ap phi p x2, and so on, up to the last point, which is ym. It is f of xm, again parameters, a1 phi 1 xm plus ap phi p xm. And now, how do we write this system in the matricial form? Try to think a bit. I will wait for some time that all of you can take a short thought about how to translate this system into matricial form. Because this is crucial. So we can write a linear system in the matricial form. However, we won't be able to write a nonlinear system in this form. So from here on, things will be different from linear and for nonlinear systems. So our goal is to write this system in the form ax is b for appropriate a and b. So for appropriate a, x, and b. And yeah, here confusion can occur because this x here in ax is b doesn't have anything to do with those x's above. So ax in b for appropriate a, x, and b. So we have to determine what is a, what is x, and what is b. So this a is matrix. As always in such equations, x is a vector of unknowns. And b is a vector of knowns, a vector of numbers which are known.
can we put all the phi's in the A matrix and all the A1 to AP in the X matrix?
Yeah, that's true. Yeah, this is exactly true. Because as we've said before, that our unknowns are those parameters, A1 up to AP. So this is our vector of unknowns. And then what's left are the coefficients which are put in the matrix A. And the vector, which is already determined vector of numbers, are those y's. So what we do A. So A is, let's start with X as you've said. So X, our X is then a vector of unknown parameters, A1 up to AP. So this is a vector, a P tuple. Then our A, matrix A, is a matrix of those coefficients appearing in those linear equations. So we have first equation, we have phi1 x1. I just read here from this first equation. So the first coefficient is phi1 x1. Then the second would be A2 phi2 x2. So phi2 x1. So the second coefficient would be phi1 x2. Phi2 x1. And then the third would be phi3 x1, and so on. The last would be phi p x1. And then I do the same for the other equations. So I have in the second line, we have, again, phi1 up to phi p evaluated in the point x2. Phi1 x2, phi2 x2, phi3 x2, and so on, phi p x2. And then in the last equation, the same is done for the last point. So phi1 xm, phi2 xm, phi3 xm, and so on, phi p xm. So what's the dimension of our matrix? So this matrix A is of dimension, it has the same number of rows as the number of the equations. So it's M. And it has the same number of columns as the number of our parameters. So it's P. And what remains is this right-hand side of the system, which is just the number of values. And this is the number, in this vector, we have y's. So vector B is y1, y2, up to ym. So it's a vector from r to the power of m. It's m tuple. So AX is B. It's the system M times P matrix A multiplied by P times 1 vector of unknowns. And as a result, we get M times 1 vector of knowns. So this is the linear system which we need to solve. So it's not, you can see that it's not a square system. If the number of equations is bigger than the number of parameters, as is usually the case, then the system is rectangular. So it has more rows than columns. It can also happen that the other case is true. So it could be that we had less equations than unknowns. In that case, this system would have more columns than rows, and it would be called underdetermined system. And from now on, we will see how to solve such a system by the method of generalized inverses of matrix A. So if this system, if A would be square matrix, and if the matrix A would be invertible, then the solution would be just X is equal to inverse of A times B. However, when A is not invertible, or when A is not even a square matrix, which is usually the case, then we cannot talk about inverses, but we will define generalized inverses. And it will turn out that in that case, the solution of this system is X is equal to generalized inverse times B. This is one of the solutions, and all the other solutions can be obtained then to just sum, to add to this specific solution, to add some vector from the kernel of the matrix A. Okay, this is just for the introduction into the chapter of generalized inverses. Are there any questions? Okay, then let's do a break till 11:30. Okay, let's proceed. So what was the main conclusion of the last hour? So we defined a linear model. We said that a function is called a linear model if all of the unknown parameters occur only in the form a1 times something which is known, and this which is known can be a function dependent on the data. We then transformed this linear model into the matrix form. So here in the matrix form AX equals to B, here X was this vector of unknowns, A1 up to AP. Then A was this matrix of coefficients. So this is first row corresponds to the evaluations of our phi's in the first point in X1. And then the second row corresponds to the evaluations of our phi's in the second point, and so on. And B is just the vector of right side, so of the values Y which have to be met in the corresponding point X. And we got this linear system AX equals to B, and know that this A doesn't need to be square matrix, but it's a rectangular matrix with M rows corresponding to the number of equations and P columns corresponding to the number of parameters. And from now on, we will see how to solve such a system from the perspective of linear algebra. We will generalize what you know about inverses of square matrices to inverses of rectangular matrices. But only to repeat what you know from linear algebra, I would like to ask you what you know about the solution of the existence of solutions of such a system. So let's try to answer on these questions. When is the system AX equals to B solvable? So what's one of the possible conditions which can be checked, or even this is the characterization of the existence of solutions of such a system? So what is this crucial condition which tells us when we will have solution and when we won't have a solution? Can you try to think about, and I would ask you to unmute yourself if you know, or just write in the chat. So you wrote, Nate wrote square and full rank. Yeah, this is true. Yeah, if A is square matrix and if it's of full rank, then there will be the solution will exist. In this case, it will be unique because X will be then just A inverse times B. So at least for this, we know that the solution will exist. But what about in general? We can answer this question very in one line for a general matrix A and for a general vector B. And A doesn't need to be square. Maybe I can help you. So it helps that to write A as a matrix with columns A1, A2. Okay, I used A1 up for A2 up to AP for parameters, let's say capital A1, capital A2 up to capital AP. So these are columns of A. Yeah, that's true. So the solution, when does this AX is B, when does the solution exist? So if we use this notation, if you use column notation of A, then AX is just a x1 times the first column of A plus x2 times the second column of A and so on, plus xp times the pth column of A. So this is the general vector from AX. And the system AX is B is solvable if and only if B is of this form. So AX is B has a solution if and only if B is of this form, so B belongs to the column space of A. I will write C of A, and C of A will stand for all vectors of this form. So C of A, we will write C of A for all vectors of this form. So XA I1 plus so on plus XP AP. And here x's vary. So x1 up to xp are real numbers. And we say this C of A, it's column space. We will denote this with C of A and say that it's column space of A. We will use it in the remaining 3 weeks. So C of A will mean this column space of A. Okay, so this has a solution. System AX is B has a solution if and only if B is in the column space of A. But how do we check if B is in the column space of A? How do we check this without solving? So let's say we won't solve this. We only need to know if the solution exists. There is one rank condition which tells us when B is in the column space of A. So how are these ranks connected? So we have matrix A, and we have matrix A, and we extend it. You probably remember that when we solve such a system, then we are solving the extended system by just adding one vector. This is the vector B. And what does has to be true for the ranks of those two matrices? If we want that the system AX is B is soluble.
The ranks have to be the same?
Yes. We have rank of A, exactly. So rank of B, rank of extended matrix. And so rank of A extended with B can be either the same to the rank of A, or it can be one bigger because we add one column. So, but the system is solvable if and only if the ranks are the same. So if the ranks are the same, if and only if, so the ranks are the same if and only if B is in the column space of A. Okay, and let us denote this rank for the moment by R. Okay, and we have P, so R is the rank of A, and P is the number of our unknowns. What can we say about when is the solution unique? When is the solution of AX equals to B unique? So now we already know when the solution exists, exactly when this condition is true, when the rank of A is equal to the rank of the extended matrix. But what can we say about the uniqueness of solutions? This will be also an important question in the continuation. So when is there only one solution and when we have some line or plane or even space of solutions? And it has something to do with R and P. So if P is smaller than R, then the solution won't necessarily exist, because the solution will then exist only for those B's which will be the combination of this form with some x's equal to 0. Because if we really need so if A is of rank R, and to express B, if we really need R columns, then we must have at least R those x's. So in general, P has to be at least R for the solution to exist. But when can we say that the solution is unique?
When it is exactly R.
Yes, when R is exactly P. Yeah, so exactly when R is equal to P. Because otherwise, if you have more than P, more than R unknowns, then we can just, so if P is bigger than R, then we can choose the value of at least one X, let's say XP, when we can choose the value of at least one X I, and still have R remaining more R or more remaining unknowns, and we will be able to solve such a system and still be able to solve the system. But when R is equal to P, then we don't have this freedom. Those parameters are completely determined. Okay, now we know when the system is soluble, and we also know when the solution is unique. We repeated this from these facts from linear algebra. And before going to generalized inverses, let's repeat also some facts about usual inverses of the matrix. So let us fix a matrix, a square matrix A. So this time it's n by n matrix, which is invertible. That means that there exists a matrix B of the same size such that AB is identity, and it turns out that then also BA is identity. And it turns out it's easy calculation to show that this B is unique. We can do it as the first proof in this course. So let's prove the first proposition. If A is invertible, then the inverse is unique. That means that there can't be two different matrices which are both inverses of A. So how would you prove this? Proof. Does anybody have an idea, or does anybody remember? It's one-line proof. How would we show that the inverse must be unique if it exists? So how would you start such a proof? You would like to show that the inverse is unique. And how would you start the proof? So let us assume that there are two inverses, and we will show that they coincide. Yeah, by contradiction. Yeah, that's true. So by the way of contradiction, we assume that there are two inverses. So we assume that B and C are both inverses of A. And what we want to show, that they coincide. And the only thing which we can use is these two equations. So this is the only thing which we can assume. I mean, the only thing which we know. So let us write 1 for B and C. There is no other way to start this proof. So we have to observe those two equations and try to prove that then B must be equal to C. AB is BA is identity, and also AC is, say, CA is identity. Does anybody have an idea what to do? I see one proof in the chat by Matej. Let's see. So Matej says that AB's identity is AC, is BA. And then he writes BAB is BAC, which means that B is C. Yeah. So what Matej does is he multiplies both of those lines by B. And let's do the same. So we have AB is equal to AC is equal to identity. So this is, I've used this, and we know that both of these are identity. That's why they are equal. So I used those facts. And then, as Matej suggests, we multiply this by b. We multiply this by b from the left. And what we get is BAB is equal to BAC is equal to B. Okay? And what we notice here, in fact, we don't need this left-hand side anymore because we needed this left-hand side only to establish that AC, so to establish that AC is equal to B. And what we can do here, so we have here, we only need to observe this part. And what we see here, if we look at this BA is equal to identity. So we use that this is identity times C is equal to B, but the identity times C is C. And this is the end of the proof. And to denote that it's the end of the proof, we use this square. Okay, maybe I've lied before. I said that the proof is one line. Yeah, the proof Matej wrote in the chat is really one line, but I wrote here a little bit longer explanation so that it's easier to follow. So the idea was only to use those two systems and multiply it by B. And once use this violet equations, and then to conclude, also use the blue one. Is this clear, or do I need to repeat some part? Okay, I assume it's clear. So if the matrix is invertible, then its inverse is unique. And before we define generalized inverse, I would only like to ask you to tell me few equivalent conditions about invertible matrices. So a matrix is invertible if and only if one of the following equivalent conditions hold. So equivalent conditions, this means that if one holds, then also the others hold. So there are at least 6 conditions which describe the invertibility of the matrix A. So I will start with first. So A has an inverse. This is just the definition. And the second is what we've just proved. So A has a unique inverse. Of course, if it has a unique inverse, then it also has an inverse. But we've proved the other direction. If A has an inverse, then the inverse is unique. So what we've proved with the previous proposition is that 1 and 2 are equivalent. But there are at least 4 more ways to express that the matrix is invertible. And I would like to ask you to remember one of those. Yes, one of the conditions is that the determinant of A is different than 0. what can we say about the image of A? Yeah, the one of the condition is that the rank of A is full, so it's n. What can we say about the column space of A or the image of A? Yeah, Nate says that squares, so that rows and columns are linearly independent. That's true. Rows are linearly independent, which is equivalent also to the fact that columns are linearly independent. So here, what can we say about the column space? So the column space should be the whole space of n tuples. So the column space is everything. And there are a few more. For example, what can we say about, yeah, another way of saying what I've said is also that the dimension of the column space is n. What can we say about the eigenvalues of A? Yes, eigenvalues of A are non-zero, are all non-zero. And what we've already said, that AX is B has exactly one solution for every B. So I thought we will write 6 conditions, but we found 10 of them. So thank you for your help. So we have 10 equivalent conditions which all characterize when a matrix is invertible. So I assume that you all know what's this linear independence of the vectors and what are the eigenvalues of A. So if someone forgot, then just ask me and I can repeat. So whenever I use some term which you forgot about the meaning or you haven't met it before, just interrupt and I will explain again. Okay, and we are almost run of time. So just to make you a little bit curious, I will here write what would be the definition of the generalized inverse. So we know that invertible matrix A satisfies A times A to the power of -1, so A inverse is equal to A inverse A equals to identity. And we would like to somehow generalize this to non-invertible matrices and also to non-rectangular matrices. Of course, we cannot expect that this equation will hold. But the idea is that if I multiply this by A from right, let's say, so I get A times A to the power of -1 times A is equal to A. And I can require that instead of A times A to the power of -1 one is identity, I can require that this equation is satisfied. If you are talking about invertible matrices, invertible square matrices, these two things are equivalent. So if A times A inverse is equal to identity, this is true if and only if A inverse A is equal to A. So these are equivalent. However, this also works to generalize the notion of invertibility for non-square matrices and non-invertible matrices. So only the definition, and then we proceed next time. So G with M rows and N columns is a generalized inverse of a matrix A with N rows and M columns if AGA is equal to A. So note that we had to change. So we start with A with N rows and M columns. And for the generalized inverse, to satisfy this equation, we have to switch the number of rows and the number of columns. So then we have N times M, and then M times N, and then again N times M. And this enables us to calculate the product of those three matrices, and the solution is, again, N times N matrix. Okay, this is all for today. Next time, we will show that every matrix has a generalized inverse. We will also show that it's not unique, as opposed to this usual inverse of a matrix. And we will see how generalized inverse can be used to solve linear equations AX is B. Okay, are there any questions for the end?
Yes, I have a question just for the upcoming lectures. Do we have to install any of the software like MATLAB? Like how soon?
So you can install Octave. It's free. So for MATLAB, you should get a student license, but Octave will work well. So you can use Octave on lab sessions. So you can just install Octave. Otherwise, you will do it at the beginning of lab session. But if you do it in advance, then it will be great. Yeah, you will spare 10 minutes of time at the beginning. So please install Octave, yeah, till Monday or Tuesday.
Okay, thank you.
Okay.